Hello again. Today we're talking about acid-base reactions. Now I know that you already know a little bit about acid-base reactions, but let's remind ourselves of what it is that we already know. Chances are you know that it's called a neutralization, although we need to be careful about that because that puts two ideas into our heads that might not be correct all the time. The other thing you probably know is that when you mix an acid and a base, you get a salt and water. And what we get for a salt might be the thing that we commonly call salt, in this case sodium chloride, but it could also be some other kind of thing because chemically the word salt means the ionic compound from an acid-base reaction, which we can then further extend to talk about pretty much any ionic compound because you could come up with some acid and some base that would produce that compound. And I said there's a couple of ideas that we could get into our head that would be incorrect. And the one thing is that the result of a neutralization reaction will not necessarily be a neutral solution. So we've already talked about strong acids and weak acids, strong bases and weak bases. And depending on the particular combination that you have, you may or may not end up with a neutral solution. You'll still call that process a neutralization. And the other thing is that when you start using certain bases, and weak bases particularly, you could end up with not a salt and a water, but in this case, just the ionic compound. And it's really because what we think of as things that have basic properties don't necessarily have to have a hydroxide. Sometimes they get their basic properties through something else. We're not really going to worry too much about number two, but number one will be a little bit of our focus, but also the math behind some of that, and also I suppose partial neutralizations are what we're talking about today. Well, if you were actually going to do a neutralization from a chemical point of view and do it with a degree of accuracy and precision, you would do what's called a titration. And the typical setup for a titration is this, and we're not going to get into the details right now, but you have a glass tube that has graduations on it. That's called a burette, and you put either the acid or the base in it. For the sake of this one, let's say it's the base. So you'll be able to measure a volume of base quite accurately. In the flask below, I know it's called something different here, you put the other one. So in our example, this would be the acid, and you'd probably put in something else. And then you have a way to mix it. We're not going to use a flea or a magnetic stir, but that's the basic setup. And what's important there is that we know 3 out of 4 things. We need to know 2 volumes, so we have to carefully measure volumes using our equipment. And if we know one of the concentrations, we will then be able to make use of the fact that in a neutralization, the number of moles of acid equals the number of moles of base. And because in most cases they're going to be solutions, the way I calculate numbers of moles of acid is the concentration times the volume, and I'll do the same thing for the base. Now if I know 3 out of those 4 variables, I can solve for the 4th one. And in most cases, what we're going to be solving for is an unknown concentration. Not all the time, but most of the time that's going to be our focus, is trying to solve for an unknown concentration. Now it won't always be 2 solutions because some acids or some bases can be solids, but we'll still be finding the numbers of moles. Okay, now the question here is partial neutralization. If I take an acid and I mix it with a base, it's working toward a neutralization, but I don't know for sure if it actually is a neutralization. So that's kind of where we're at today. So the typical kind of question you'll be looking at is this one, where I'm given a volume and a concentration of both the acid and the base. Now if you look at this one, you'll notice that the concentrations of both solutions are the same, but the volumes are different. So obviously the numbers of moles of one is going to be different. So how do I do that? I can probably expect that you know that this will not be a proper neutralization, but a partial neutralization. It's a little bit like doing a limiting reagent question from several weeks ago, except in this case, what we want to know is not what's limiting, we want to know what's in excess, because the thing that's in excess is going to control the pH. So I have a reaction and I have a concentration and I have a volume. Well, how do I work through the math? Well, that's coming up. So taking those ideas forward, taking those numbers forward, we're going to calculate numbers of moles of acid, and we're going to calculate numbers of moles of base, and you'll notice, as we predicted, they're not the same. Okay, so one of them is a little bit more. We have a few more moles. Well, that's the one that we actually want to pay attention to, the one that has more numbers of moles. So how many moles of excess is what I need? So I calculate numbers of moles of excess, take the big one minus the little one. It's important to keep track of whether that big one is an acid or a base, because that'll change what we do later. Once I know numbers of moles of excess, I'm not quite ready for a pH. Don't forget, pH requires a concentration. So now I take that numbers of moles of excess reagent and I divide it by the total volume, because I've mixed those two solutions together. So now I've got more volume. So I put the total volume in there. Now I have a concentration. Now I can calculate a pH. Now in this case, it's the pH of an acid, so it's a one-step operation. But you will often have a pH of a base, as you know, where it's a two-step operation. So how we go about it is right here. And it's really not that, it's a long process and it's kind of involved, but it's not that difficult. And if you think it through, it's, I think, fairly obvious. Numbers of moles of each reagent. I'll have more of one than I'd have of the other. How much extra do I have? Okay, what does that mean for the concentration? And then what does that mean for the pH? Don't forget, because this is where a lot of people are going to get stuck, if you are calculating the pH of a base, you have to first find the pOH before you can find the pH. Okay, we're going to take one more to work through. Please pause it, write this down, work it through, and then we'll hopefully catch answers or compare answers on the way through. But you're first going to find numbers of moles of acid, numbers of moles of base, whichever one is in excess. In this case, it's the base, so that means don't forget, right now we should be thinking about, okay, what does that mean for my final answer? And then calculate the new concentration, don't forget that step, and then find the pOH, find the pH. So it takes up a lot of space, kind of long, but not that difficult. Okay, this one I'm not going to show you the answer, so we'll talk about this one in class. Maybe it'll be a hand-in class when we get there. Pause the video, write it down, and then we'll wrap up with a few final comments. Okay, sorry about this. It just tells me when I'm done, and it's an easy way to do it. When we talk about neutralization, it's important for us to remember which ones are going to be a full neutralization and which ones are going to be a partial neutralization. The question look is going to be, I think, obvious enough. If you see two concentrations and two volumes, then you can easily calculate numbers of moles. If you don't have two concentrations, then usually the question will be, what is the new concentration, rather than what's the pH? Then you're going to be doing numbers of moles of acid equal number of moles of base, and then it will be a full proper neutralization. For us in this course, we're not really going to worry too much about, well, what if it's not a neutral solution? That's a job for another time and another place. Talk to you in class.